Hello everyone, my name is Patiste. I am a first year master course from Uchida Laboratory, and today I'm going to talk about the 3.7 part of the paper we are studying, and this part is about mechanics of young concrete before cracking. Here are the contents. There are 4 parts in this section. So the first one is about particle dispersion and solidification. Second one is about modeling of solidifying cement paste. The third one is about coupling of skeleton stresses and poor water pressure. And the last one is about simulation and verification. Actually, what I'm going to talk about is only 2. The first one and the second one. So let's get started. I think we all familiar with this picture. For the actual practice today, of course, when we design concrete, we design in a larger scale. But in the paper, we are trying to understand, or we are trying to study at micro level, what happened at the micro level. And for my part, the size of the micro level is from micrometer to centimeter. Before going into the paper, first I would like to review what we have studied when we were in bachelor degree. So here the first, the basic knowledge about solidification of concrete. Concrete does not need to dry out in order to harden as commonly thought. The concrete needs moisture to hydrate and cure. When concrete dries, it actually stops getting stronger, which means the properties of dry concrete is would be less than of the wet concrete. The reaction of water with the cement in concrete is extremely important to its property, and reactions may continue for many years. Only the calcium silicates contribute to strength. 3 calcium silicate is responsible for most of the early strength, for example, for 1 week. Here is the very common equation of hydration of cement. So we have 3 calcium silicate added by water. Then the result, we have calcium silicate hydrate plus calcium hydroxide and then heat. Then let's move on to the introduction from the authors of the paper. So the degree of hydration and moisture in micropores influences the solid mechanics of cementitious composites. And this, I think we can understand this from what we have studied at bachelor degree. A high-level engineering judgment is required on such an ambient-related parameters and 3D shape of structural geometry, since the local moisture conditions and micropore development are not explicitly known in computation. So here the authors try to claim the importance of modeling microscale structure. Volume of cement paste matrix is highly associated with moisture migration, and unlike aggregates, volumetric interaction of aggregate elastic particles and paste matrix is one of key issues when we construct overall space average constitutive modeling of concrete composite. Then shear deformational mechanics is thought governed by matrix with less contribution of suspended aggregates. So when we model the aggregate in smaller scale, we consider aggregates as suspended solids or suspended material. Let's go on to the first part, which is about particle dispersion and solidification. Dispersion is terms used in statistical study. We can say in simple word is we can say that variation or differences. Solidification means getting become harder, become hardening. So here's the concept of modeling of concrete composite. Aggregate particles can be modeled as a suspended elastic body by surrounding cement paste as shown in this picture, and local stresses developing in both aggregates and cement paste are non-uniform. When hydration starts, solidified layer is bound, and when hydration continues, new solidified layer is bound. Here the authors define the referential volume, or EV, whose scale is about 1 to 5 centimeters, and it includes several gravels and sands. The volumetric acted on concrete can be calculated by this equation, and the volumetric strain of concrete can be calculated by this equation. Here Ag means aggregates and Cp means cement paste. Volume fraction rho is the ratio defined by a volume of a material divided by referential volume. Here are the equations I mentioned earlier. For aggregates, the relationship between stress and strain can be written like this, where Kag is the stiffness of the aggregate. But for cement paste, it's not like that. It's not that easy because it related with time changing according to the hydration. So we will consider it from now. By the way, for the local equilibrium and compatibility between the two elements, between aggregate and cement, can be written like this. Stress divided by stiffness is equal to strain. So here is the inner strain, and this one is outer strain. So the summation of these two must equal to 0. And again, the equation, the local equilibrium between the two elements like this. And from this equation, we can say that if the cement paste matrix be a perfect liquid that loses resistance to the shear deformation, so we can have stress of aggregate equal to stress of cement paste. In this case, the shear stress of the cement paste becomes 0. If in opposite way, if the shear stiffness GCP is infinitely large, it brings no change of geometrical shape and results in strain of aggregate equal to strain of cement paste. Here are something we need to know before we go further to the calculation. Under the deviatoric shear mode of deformation, shear stress is hardly transferred through the contact link with network of aggregates except for prepackaged concrete, and rotational resistance of individual particles is no longer expected when cement paste matrix deforms in shear. The authors assume that the space average deviatoric stress and strain of cement paste in concrete coincides with those of overall cement composite. So the relationship between deviatoric stress and strain tensors for both cement paste and concrete composite can be written like this. F is a function that shows the relationship between stress and strain tensors, which we will talk about it in the next slide. The structural growth of cement paste is rather complex. Upon contact with water, powder particles start to dissolve and the accent products start to form. The accent products means the solidified layers. Maybe we have shown here. Old solidified layer, new solidified layer is the reaction product or hydration product. Due to gradual solidification of hydration products, properties of paste matrix varies with time. So here is very important. The process of hydration is strictly related with time. Solidification theory proved a potential way of taking this aging effect into consideration. Here is how they do the model of the material. For example, it's the microstructure at early age, look like this. So when the hydration started, many hydration products started occurs, and again migration at old age it become even more larger, the number of the materials, and we can simplify it like this. It's the connection of the material can be simplified like this. Each material has its own stiffness and characteristics like E and C. Okay, at this time, for example, at this time there are only 4 tire materials here, but when the time changes, when the times keep on going, many others microstructures started occurs. So we can say that growth of cement paste is idealized by forming finite fictitious clusters. Fictitious cluster mean the cluster, just a made-up cluster, is not the real cluster. When a new cluster is formed into the already formed assembly of old cluster, a group of old clusters, and then strain of the cluster is originated at the time of birth. Yes, as I have mentioned before. Aging process is represented by solidification of new cluster afterwards. So in order to set a criterion for cluster formation, a volume fractional function is introduced. It looks like this. Phi t is the hydrogen ratio at a time, so we can calculate by using hydrated volume of cement divided by the total volume of cement. So phi t is very important, hydrogen ratio at the time, so let's also remember it. Again, the structure of cement paste at any time is represented using the number of clusters already solidified at the time. According to hydration degree, numbers of clusters and at a certain time can be determined, and when the hydration increment reaches a certain value, a new cluster is developed and attached to the older ones. As these clusters share bearing stresses carried by the cement paste, they also introduce an infinitesimal stress, they mean very small stress, in each cluster, and it is written by SCP. When a new cluster is formed, these infinitesimal stresses are redistributed among the clusters, and it also means that the stress condition in a certain cluster is a function of both current time and the location of this cluster, or the time when this cluster was bound. And again, let's suppose that SCP is equal to SCP T prime T, which means the average stress in general cluster, where T is the current time and T prime is the time when the cluster is solidified. So the the total volumetric stress in cement paste at a certain time is the summation of average stresses in all clusters activated at that time, and strain in cement paste is equal to 1 induced in each cluster. The equation can be written like this, and I'm going to explain this equation in the next slide. SCP is infinitesimal stress in each cluster, and phi, as we know, is hydration ratio at the time, and sigma CP is a total stress. From here, SCP d phi, we can understand that SCP, the stress in each cluster, is depend on the hydration ratio, and so the total stress on the cement paste is also depends on the hydration ratio at any time. The second part is about modeling of solidifying cement paste cluster. The solidifying mechanical unit is thought to be associated with CSH, gel grain, CSH, which means calcium silicate hydration. Time-dependent deformation rooted in moisture in gel and interlayer pores should be taken into account in each individual solidifying component. The assembly of solidifying components corresponds to cement paste. The moisture existing in capillary pores between gel grains has to be taken into account in the model. So here is the model of solidifying cluster of cement hydrate, and here is the referential volume, and if we take one part, we can see it like this. Here it is there are many types of material combined together, and each material has its own property like stiffness, so that's why it can be modeled like this. So the author simply assume two factitious time-dependent deformational components rooted in both interlayer or gel pores and capillary one. Moisture transport actually takes place into the capillary and gel pores under severe drying. Interlayer water starts to be in motion. Thus, moisture transport related to each of these pore categories can be correlated to a certain aspect of the creep behaviors. The rate of flow of capillary water is comparatively high and easily irreversible. Moisture transport within capillary pores can be assumed as a cause of short-term creep and earlier ages. This creep rate drops steeply with time and is highly related to the hydration process. Moisture transport within gel pores is thought to be slow and prolonged in nature. Kinematics of gel water can be reversible up to a certain limit. It can be assumed as a cause of long-term creep and is responsible for the main part of the undercover wall creep. Moisture migration within interlayer pores can be assumed to dry creep under severe condition. This creep is highly irreversible, accompanying by so-called disjoining pressure. So again, here is in order to reflect three aspects of creep behaviors, a simple rheological model for each cluster component is assumed. This kind of modeling is called rheological model. So the same model is adopted for both volumetric and deviatory components. Total strain of each solidifying cluster is decomposed into instantaneous elastic stress, epsilon E, and viscoelastic strain, epsilon Z, viscoplastic strain, epsilon G, and instantaneous plastic strain, epsilon L. So again, volumetric strain general is the sum of each strain, which looks like this. Each strain has its own property, so we're gonna see in next slide. For example, instantaneous elasticity, the relationship between the stress and strain can be written like this. And for viscoelasticity, stress and strain relationship can be written like this. For viscoplasticity, it can be calculated by this equation. And for instantaneous plasticity, it can be it can be written by this equation. So here's the conclusion of what I have talked, and the process of calculation looks like this. And from now I'm going to try to talk in a simple way so that you can understand what I have taught today. So by using the FEMS structure information such as dimensions and shape, etc., and environmental conditions such as relative humidity and temperature can be obtained. And for microphysical information, which are computed at all cost points of the mesh, say just temperature degree or hydration degree, porosity, saturation, viscosity, and pore pressure. Then we need to assume the strain tensor, which looks like this, and you can understand that this is the strain on x plane, this is the strain on y plane, this is the strain on z planes, and this guy is the strain on the shear plane or shear component. After that, we need to determine the number of cement paste layers. So as you can see here, at the core position there is no hydration phenomena, but when the hydration started, we can get the inner product. The product is the hydration product, and when the hydration continues, and we can get the outer products. So this layer just keep on growing bigger and bigger. When we do the calculation, we need to determine the number of these layers. After that, we need to divide the consideration into two aspects. And the first one is volumetric component, and the second one is deviatory component. As I have mentioned before, that at very small scale, the stresses that act on the concrete is not uniform, so we cannot use direct stress, so we need to use the statistical value. And in this study, the author used the mean value as the calculation, so that's why here we have mean strain, which looks like this. And then first we need to, for further calculation, we calculate the compatibility and equilibrium condition. It looks like this. So the strain of concrete is the summation of the strain of aggregate and the strain of cement paste, because strain is related with the volume fraction of each material. That's why the volume fraction rho is introduced in this equation. Then for the strain of aggregate, we can calculate by this equation. It's very simple. For cement, it's not that simple, and the basic calculation is like this. And the total stress that act on the cement paste can be calculated like this, which can be explained like the total stress that act on the cement paste is the summation of the very small stress SCP that act on the clusters of cement paste. And psi is the hydration rate. So the total stress is strongly related with the hydration rate. For the very small stress SCP, it can be calculated by this equation. So as we have discussed before, during the hydration process, we can model the material like this. So each material has its own property like shear stiffness and viscosity, etc. And that's why the relationship between stress and strain of cement paste can be calculated in 4 ways. So 1, 2, 3, 4. After we get this stuff, and we can apply the Lagrangian summation, which is the inner strain of the total of inner strain and outer strain is equal to 0. By solving this this 4 equation, then we can get the strain of aggregate, strain of cement paste, stress of aggregate, and stress of cement paste. And then finally we can calculate the stress that acted on the concrete. And here it is the same as here. We can say that the stress that acts on the concrete is composed by stress that acted on the aggregate and stress that act on the cement. Using these results, and we can calculate stress tensor at all coast points of the mesh, which looks like this. And after that, we need to update path and time dependent parameters for each layer. This is just the calculation at time t, but hydration depends on time, so microphysical information input to the structural computation is updated every time, or let's say must be updated every time. Okay, that's all for my presentation. I think it's not easy for us to understand the stuff that I have mentioned, and frankly and personally, and it's not easy to make a video about this paper, and it would be easier if we can talk face to face or directly, but we have no choice. So yes, just do what we can do. So if you guys need any confirmation, or you have comments, questions, please feel free to connect me, emailing me, or whatever, and I would be very happy to communicate with you with this subject. Yes, it's very hard to explain. So thank you very much for your time, and see you all.